So I'm going to give you a very, very brief intro on just some things to think about as you start. This is really the start of the session. We start in the middle with architecture. And let me first say, I really enjoy hiking, and I enjoy taking trips. And this is a remote place in New Zealand. You can see where the path goes up. But the strange thing is that wherever you go now, you're getting closer, and the electronic world is moving in. So even almost at the peak here, you have good line of sight, and you can get a cell tower. And it's amazing to see people hiking up paths like this and looking down at their phones and either posting to Facebook or checking email when they have this to look at. So I am going to make the same recommendation to you, which is that you have 2 weeks, not quite, here of instruction, and you should not spend that time reading your email or doing IM or posting to Facebook. When you're in the room here, the people who have prepared their talks, you should be preparing questions. I mean, really hard questions for them, and taking notes to the best of your ability. So really take the time this week to dive in and suck the marrow right out of this program. Take as much as possible out of the program. So we're going to do a very quick review as we get started. You may have seen this picture yesterday. This is the Avodac, which was the first computer that Argonne had, 1953. This is Gene Hall programming, and of course you program it with switches. And the reason I pull this up is that this is in 1953, and 30 years later, after this first computer, which is what the physics department had put together, we have a computer science department and at Argonne, so 30 years later. And if you look carefully at this picture, you should see at least one person in the room here who was in that picture. I'll give you a hint. It's kind of in the middle, and he had a beard at the time. I think later, we might see on the left, I don't know if you recognize Jack Dungera. So he is someone who is very well known in high-performance computing, was at Argonne at the time, and I think Rusty will be speaking later this week, and so he's also in the picture right next to Jack. So 30 years later, a computer science department is born from that first computer, and then 30 years later, we continue. We have summer institutes sponsored by NSF, and now, 30 years later, 2013, is the beginning, the launch of this training program. And so Argonne is very dedicated and interested in computing and in the software and the hardware from the very beginning, from building machines and now the kind of machine we have, Mira. And what I want to do as we talk about architecture, this is one of the founder of IBM, Watson, and he had a sign above his study there that said think. This is a very famous picture and a very famous word, think, and it was then replicated in IBM all over the place. And what I'm going to ask you to do, especially in the hardware session and the rest of the week, is think very, very carefully about your model for the machine and your model for the software. So one of the key things in computer science is that we create abstractions that match some model. And you might have a Newtonian model, some sort of very simple model, and then you realize that in the edges, that model breaks. So we have things in our model, and especially as we talk about the hardware, that creates something that then you code to that makes the shape of the program. So an example is you might initially start out and you think, okay, memory is flat. I access memory. No matter where I access memory, it's the same speed. Well, of course, that's one model, and we know that that's not really how the world works. We have other things. We have NUMA. We have cache. The same thing is true for power. The same thing is true for data movement. And you'll hear from Pavan on interconnect. So spend some time as you're looking at your code and as you're thinking about the future and how you write programs, understanding what your model for the machine is and where that model breaks. And so in all of the speakers today, ask yourself, and in fact you could even ask the speakers that question, okay, what do we have, what do we hold in our head as the model, and then where does that model start to fall down? What are the ragged edges where, for example, there are places where caching does very poorly, right? And so that's where the model breaks. And that's where, as a programmer writing code, you really need to understand that. So I used to work at Los Alamos, and I worked for someone at the time named John Reinders, and he had this quote, the average time required to implement a moderate-sized application on a parallel computer is equivalent to the half-life of the latest parallel computer, which means you spend about half your time working on the code, and then you get the last half of the life of the machine to use it. So it's very important that as you work this week and as you look at the hardware, that you get the abstractions that let you not just implement to the hardware, but you're creating a framework, a portable framework that for several generations of machines is useful to you. So with that, I'm going to wrap up with just a couple slides. These are my recommendations for this week. So you look at this week and the hardware and the software talks. First, we're going to start with OPM, Other People's Math Libraries. It is surprising how many times people decide that they are going to write a dense matrix loop or a sparse matrix solver or something, when really they could use someone else's fantastically optimized math library. Not just math, but all libraries. So start with that. Make sure you have that in your code recommendation. Figure out how to encapsulate your parallelism and your messaging in I/O. And hopefully later this week you'll hear more about encapsulation. You already know a little bit about it. But really struggle with how to keep your model for your parallel program such that you can change how parallelism is expressed and you can change the back end on how that's put to the machine. The same for messaging and I/O. It's also, when you start a program, there are little things that you have to start adding as your code base grows. And embedding those capabilities from the very beginning is very important. Debugging, performance monitoring, correctness detection, and resilience. These are all things that when you first write that little 30-line kernel, that's fine. But then as you start to evolve that into a framework, these things have to be embedded. So spend this time this week looking at all the different talks. You'll hear a talk on tools. You'll hear a talk on performance tools and on debugging and so forth. Figure out how you embed that into your framework. So at the very beginning, everything is in. There are two kinds of workflows, the workflow of the science and the workflow of the programmer. Understanding these two workflows and how they interact is key to being able to sustain a large project, a large code base. Also, it's very worthwhile to invest in automation. From the build system and nightly tests on to versioning and including metadata in your source code so that you can run one of these source code tools and extract information about your program. This is all extremely worthwhile to invest. And then, of course, there's the larger community. So with that, I'll point out some things, again, in this investment space. So things that are trending up as we look over the last couple years in hardware and in software. Asynchronous behavior and the need for latency hiding is trending up. So as you look at your code, these are important things to invest in. Block synchronous is kind of trending down, and in my talk this evening at dinner, I'll talk about why. Over decomposition and load balancing, again, to help with that asynchrony. Trending up, massive parallelism rather than countable parallelism, where you select, I have P processors, and therefore my work will be divided by P. That's countable. Hierarchical memory instead of flat memory. Again, this abstraction of this model abstraction of flat. Very expensive data movement is what is trending up, sadly. It means that every distance that you move your data is a cost. And being able to understand that, and again, have that in your model for how a computer works is important. These sort of, the opposite of that was in the long ago, years ago, were expensive flops. where people worried most about counting flops and how to reduce flops. Now we have algorithms that increase flops and reduce data movement, reduce moving data off or to memory. A fault and resilience strategy instead of just checkpoint restart. There are a lot of new algorithms and new techniques for finding out how to move part of the data to nearby nodes, to use other advanced strategies for resilience rather than just sort of checkpoint the entire machine. And finally, looking at and analyzing some of your data while it's still in the computer, in situ, rather than sloshing it back to the file system and then sloshing it back into the computer. Can you do any of that analysis, any of that computation on the output data right there in the computer? So with that, this morning and then part of this afternoon, we'll be diving into both the messaging and the hardware, how chips work, GPUs, CPUs, and then later we'll be going into message passing. So with that, I think we have a minute or two if there are any questions. Remember, one of my first charges was come up with good questions. You can tell more from questions than from answers, right?